Somewhere out past the edge of what most telescopes can see, there are objects that were built exactly the way every star in the sky was built, out of the same collapsing cloud, under the same crushing gravity. And then, partway through, something stopped. Not a planet, not a star. For decades, astronomers could not even agree on what to call the objects they suspected were out there, let alone prove one existed. Some of these worlds may be closer to us than almost anything else in the night sky, and one of the very first ever confirmed has spent nearly 30 years hiding something that only the newest instruments on Earth were finally able to see. Tonight, we go looking for what it means to almost become a star. If you want content like this, a like and a subscribe is a small way of saying so, and it genuinely helps this channel reach more people. Get comfortable now and let your shoulders relax. In 3, 2, 1, lift off. Look up on a clear night, away from the glow of any city, and you will see thousands of small points of light scattered across the dark, and it is easy to assume every one of them is doing the same thing, burning, shining under its own power, the way our own sun does, the way every star strung across the winter sky does. That assumption is wrong more often than most people realize. Scattered among those true stars, hidden in plain sight, are objects that never earned the right to shine at all. Astronomers who study them have taken, somewhat unofficially, to calling them failed stars, and for once, the plain language is not far from the truth. They formed exactly the way every star in the sky formed. They simply never finished the job. To understand what failing actually means here, you first need to understand what succeeding requires. A star is not defined by how big it looks, how brightly it shines, or how long humans have had a name for it. It is defined by one specific event deep inside it that either happens or does not. The moment hydrogen atoms are forced together with enough heat and pressure to fuse into helium, releasing light and warmth that can sustain itself for billions of years. That moment depends entirely on how much mass a collapsing cloud of gas and dust manages to gather before gravity finishes pulling it into a single dense body. For an object built from roughly the same elements as our Sun, the dividing line sits at approximately 80 times the mass of the planet Jupiter, the largest planet in our own solar system. Reach that mark, and hydrogen fusion ignites, and a star is born. Fall short of it, even by a small margin, and hydrogen will never fuse inside that object, not in 1,000,000 years, not in 1,000,000,000,000. Here is what makes the story stranger, though. There is a second, lower threshold, one almost nobody outside the field has ever heard of, sitting at around 13 times the mass of Jupiter. An object that clears this lower line but never reaches the upper one can manage a much smaller, weaker version of fusion, burning a heavier form of hydrogen called deuterium instead of the ordinary kind, for a relatively brief stretch of its early life, before that limited fuel runs out completely and nothing replaces it. For a while, an object like this genuinely does shine from its own internal fire. It is also nowhere near enough. Once that early fire burns down, it can only cool and dim for the remainder of its existence. It is not a planet, because true planets do not form through the collapse of a cloud this way. It is not a star, because a star's furnace, once lit, does not go back out. For a very long stretch of the 20th century, this in-between category sat entirely unnamed, because nobody had needed a name for something nobody could prove existed. The idea that such objects should exist at all was first worked out mathematically in the early 1960s by an astronomer at the University of Virginia named Shiv Kumar, who spent years working through the equations describing how a collapsing cloud's core temperature and pressure change as it gathers mass, and calculated well before anyone had a telescope capable of testing the idea precisely where the upper threshold had to sit. Working independently around that same period, two astrophysicists in Japan, Hayashi and Nakano, arrived at almost the identical number through their own separate calculations, unaware of Kumar's work until afterward. Kumar called his theoretical objects black dwarfs, reasoning that anything failing to ignite proper hydrogen fusion would simply sit in permanent darkness, growing colder and fainter with every passing year. The name held for over a decade, until a young astrophysicist named Jill Tarter, who had come up through a world that made very little room for her, moving from an engineering physics degree at Cornell University in 1965 to doctoral work in astrophysics at the University of California at Berkeley, inherited Kumar's objects in her 1975 thesis and pointed out the problem with what he had called them. Black dwarf, she recognized, already meant something else entirely, a genuinely different and far more distant fate that, as it happens, has never actually been observed anywhere in the universe. Kumar's objects needed a name of their own, and Tarter proposed brown instead, a deliberate compromise sitting between the red, already claimed by faint ordinary stars, and the black, already claimed by that far more distant kind of darkness. Kumar was not working in isolation on some strange fringe of the field. By the early 1960s, astronomers already had a well-developed understanding of how ordinary stars live out their lives, often called the main sequence, a framework built up over the preceding several decades, describing how a star's mass determines its temperature, its brightness, and how long it will burn before it changes into something else. What Kumar, and independently Hayashi and Nakano, were doing was pushing that same well-tested framework down to its lower limit, asking a question the existing theory had never needed to answer before. What happens to an object that undergoes every early stage of stellar formation correctly and simply runs out of mass before the final step? The mathematics did not require inventing new physics. It required carefully extending physics that already worked into a regime nobody had previously had reason to examine closely, because nobody had ever needed to imagine a star that never lit. It helps to slow down and picture the actual process a little more closely. The one Kumar and Tarter's objects both begin and then abandon partway through. A star does not begin its life as a star. It begins as a cloud, cold and dark and shapeless, sometimes stretching across distances that would take light itself years to cross, doing very little for what can be an extraordinarily long stretch of time. Then, often nudged along by something as violent as a nearby exploding star sending a shockwave through the gas, gravity slowly begins to win, and the cloud starts folding in on itself, gathering into a denser and denser ball over the course of hundreds of thousands, sometimes millions, of years. As it shrinks, it heats up. The same basic principle that makes a bicycle pump grow warm as you compress the air inside it, only unfolding on a scale that dwarfs anything in ordinary human experience. Every star you have ever pointed to in the night sky represents the successful ending of exactly this process. Enough material gathered, enough collapse achieved, enough heat and pressure generated at the center to light a fusion furnace built to burn for billions of years. To even begin picturing what 80 Jupiters means, it helps to start with Jupiter itself. Roughly 11 Earths could be lined up edge to edge across its face, and its sheer volume could swallow well over 1,000 planets the size of our own. Jupiter alone is already more massive than every other planet in our own solar system combined, twice over, and even Jupiter, falls more than 70 times short of the mass. A cloud like this would need to gather before hydrogen fusion could ever ignite at its center. An object caught between the 13 and 80 Jupiter mark undergoes this exact same collapse, this exact same heating, and arrives at the exact same kind of core. It only fails at the very last step. It is worth noting, too, that not every object caught in this middle zone fails by the same margin. An object sitting just above the lower threshold, at perhaps 14 or 15 Jupiter masses, manages only the barest, briefest trace of deuterium fusion before running out of fuel almost immediately. An object sitting close to the upper threshold at 70 or 75 Jupiter masses can sustain that same weak reaction for a much longer stretch and glow with considerably more warmth while it lasts, blurring the line with true, if very small, stars even further. What determines exactly where any single object lands within that wide range comes down to nothing more exotic than how much raw material happened to be available in its particular corner of its birth cloud, and how efficiently gravity managed to gather it before the surrounding gas dispersed or was swept up by hungrier neighbors nearby. There is no mechanism singling out 13 Jupiter masses or 80 Jupiter masses as somehow special destinations in their own right. They are simply the 2 points where the underlying physics of fusion happens to change, sitting along a smooth continuum of outcomes running from the smallest, faintest true stars, down through this failed middle category, all the way to true planets, with nothing about the process of formation itself marking in advance where one category ends and the next begins. The fate Tartar was so carefully avoiding is worth understanding on its own terms, because it turns out to be almost as strange as the objects at the center of this story. A white dwarf is what remains after a star like our own sun finishes burning through its usable fuel, swells briefly into a much larger red giant, and sheds its outer layers into space as a softly glowing shell of gas, leaving behind an extraordinarily dense, still blisteringly hot core, roughly the size of Earth, despite containing a large fraction of the original star's mass, that no longer generates any new energy of its own. Left alone after that, with nothing left inside it to burn, that exposed core should simply radiate its remaining heat away into the surrounding darkness, year after year, growing dimmer and cooler without end, until it would eventually stop glowing altogether and become, genuinely, a black dwarf, cold, dark, and finished, indistinguishable from the empty space around it. Here is the detail that makes this worth pausing on. Cooling a white dwarf down that completely takes far longer than the universe itself has existed so far. Every white dwarf ever observed, without a single exception, anywhere, is still radiating measurable heat. Not one true black dwarf, in the sense Kumar first used the term, has ever been confirmed anywhere in the observable universe, because there has simply not yet been enough time, since the beginning of everything, for a single one to finish cooling. The name Kumar chose already belonged, by rights, to a kind of object that does not exist yet anywhere and will not for a very long time still to come. Brown was never meant as an accurate paint chip either. If you could hold one of Kumar and Tartar's objects up close enough to examine directly, most of them would appear a deep, dim red or something closer to a dull magenta, depending on exactly how much residual warmth they still happen to have. Tartar's chosen word was a compromise, a color sitting deliberately between the red already claimed by faint, ordinary low-mass stars, and the black already claimed by that far more distant, not yet existing kind of darkness, meant to describe something that was neither fully alive the way a star is alive, nor fully finished the way that far more distant fate is finished. Brown dwarf was the name she settled on, and it is the name that has stuck, used by every astronomer working in the field to this day. It is worth sitting with what an unusual thing this was to do. At the time, Tarter had just put a permanent label on a class of object that not one person on Earth had ever actually seen. Every star anyone had ever named, going all the way back to the earliest civilizations who first charted the night sky, was named for something people could point to directly and confirm with their own eyes. Kumar and Tarter's object existed only on paper, a mathematical prediction now wearing a brand new name, waiting for proof that had not yet arrived, and as it would turn out, would not arrive for another 20 years. Tarter herself would go on to a very different kind of recognition. In the years that followed, she helped found the SETI Institute in 1984, dedicated to the search for radio signals from other civilizations, and spent decades directing its research, pointing enormous radio telescopes at the sky and listening for a deliberate signal rather than for light, work well known enough that it helped inspire the character played by Jodie Foster in the 1997 film Contact, about the search for a message from beyond our own solar system. But in 1975, none of that lay ahead of her yet. She was simply a young researcher who had noticed an awkward piece of unclaimed scientific terminology and quietly repaired it, with absolutely no way of knowing how long it would take for the objects hiding behind that new name to actually turn up, or that she herself would spend much of her later career doing something oddly similar, listening patiently for confirmation of something no one could yet prove was there. There is something genuinely strange about a scientific term becoming common currency before the thing it names has ever been observed, and that is exactly what happened here. Throughout the 1980s, as the search dragged on without success, brown dwarf became a completely ordinary phrase in astronomy departments, used in lectures, written into grant proposals, printed in textbooks describing stellar evolution, discussed at conferences devoted specifically to the topic. Students learned the definition of a brown dwarf, learned the two mass thresholds that bounded it, and learned to picture what one would look like, all without a single confirmed example anyone could point to on a star chart. It was, in a sense, the reverse of how naming ordinarily works. Normally an object is found first, studied, and then given a name that reflects what has already been learned about it. Here, an entire vocabulary, an entire mental picture, had been built and widely adopted around something that remained, for 2 straight decades, a name in search of a thing to attach itself to. The reason a lower mass object can manage deuterium fusion at all when it cannot manage ordinary hydrogen fusion comes down to a small but consequential difference in the atom itself. Ordinary hydrogen is the simplest atom there is, a single proton with a single electron circling it. Deuterium is a heavier cousin of that same element, carrying an extra neutron alongside the proton, and that additional weight changes the physics of the collision required to force 2 nuclei together. Deuterium nuclei fuse, or combine with an ordinary hydrogen nucleus, at temperatures and pressures considerably lower than what ordinary hydrogen fusion demands. An object that could never generate enough core heat and pressure to fuse hydrogen can still, for a while, generate just enough to fuse the much smaller amount of deuterium mixed in among its material. This is why the lower threshold sits so much further down the mass scale than the upper one. It is not simply a smaller version of the same reaction. It is an easier reaction entirely, one that asks considerably less of the object attempting it, and gives considerably less back in return for a much shorter time. Part of the difficulty in ever finding one came down to simple physics of light itself. A hot object radiates most of its energy at shorter wavelengths, which is why our own sun, blisteringly hot at its surface, appears to human eyes mostly as ordinary visible light. A much cooler object radiates most of its energy at longer wavelengths instead, out past the edge of what the eye can register in the range astronomers call infrared. A brown dwarf, even during its brief window of deuterium fusion, runs at temperatures far below any ordinary star, which means the bulk of whatever light it does produce comes out almost entirely in the infrared. Searching for one with instruments built to see ordinary visible light, the kind used in most observatories for most of the 20th century, meant missing the vast majority of the very evidence that would have proven it was there. Astronomers were not just looking for something faint. For most of the search, they were looking with the wrong kind of eyes. During that brief window, while deuterium is still burning, a young object in this middle category can be genuinely difficult to tell apart from a true star. It glows. It generates real heat and real light from real fusion happening at its core, not merely from the leftover warmth of its own collapse. For a relatively short stretch, lasting anywhere from a few 100,000 years to a few million, depending on precisely how much mass it managed to gather, it can shine with something close to the output of the smallest, faintest true stars in existence. Then the deuterium runs out, nothing replaces it, and the long, one-directional process of cooling quietly begins. This, more than anything else, is what made these objects so difficult to catch, and it is worth understanding exactly why. Any object bright enough and young enough to stand out clearly against the background of ordinary stars was, by definition, still early in that brief window, easy to mistake for a small, dim, but perfectly ordinary star. And any object old enough to have cooled past that resemblance had also, by the same token, cooled past the point where the instruments of the day could reliably detect it at all. The very feature that would eventually prove these objects was something new. Their unmistakable faintness was the same feature that kept them hidden for so long. None of this stopped astronomers from looking, and in fact it gave them a reason to look harder. Beyond simple curiosity, there was a genuine practical stake in confirming even a single brown dwarf. Throughout the 1970s and 1980s, astronomers were grappling with growing evidence that galaxies, including our own, seemed to contain far more gravitational pull than their visible stars alone could explain, a puzzle that would eventually come to be discussed under the general heading of missing mass. Some researchers wondered whether enormous numbers of these faint, star-like objects, invisible to ordinary telescopes and scattered through the galaxy in numbers nobody could yet measure, might help account for some of that missing gravitational influence, hiding not in some exotic form of matter but simply in plain, ordinary material that had collapsed the same way every star collapses, and had then gone dark. Confirming that brown dwarfs were real, and working out roughly how common they actually were, mattered for reasons that reached well beyond simply settling a matter of scientific terminology. It touched on a much larger question that astronomers still had no good way of answering. How much of the galaxy's actual contents had they simply never been able to see at all? So the searches continued through the better part of 2 decades, using whatever tools happened to be available at the time, and they tended to follow one of 2 general strategies. The first was to look at young star clusters, tightly packed groups of stars, sometimes numbering in the hundreds, that had all formed from the same collapsing cloud at roughly the same time. The Pleiades, the loose scattering of blue-white stars visible to the naked eye on a clear autumn or winter night, sometimes called the Seven Sisters, is exactly this kind of cluster, and clusters like it became natural hunting grounds, on the reasoning that any brown dwarfs, born alongside their stellar neighbors, would still be in their own brief deuterium burning phase, and therefore at their brightest and most detectable, before age dimmed them into obscurity. The second strategy was to search for faint companion objects orbiting closer, better studied stars, hoping to catch one hiding in the glare of a brighter neighbor, using tiny wobbles in a star's light, or positioned to reveal something too dim to see directly. Each strategy came with its own frustrations. Searching a young cluster meant working with a crowded, confusing field packed with hundreds of similarly faint points of light, most of them perfectly ordinary young stars, with no easy way to tell at a glance which few, if any, might be something else entirely. Searching for a faint companion instead meant dealing with the glare of a much brighter neighboring star, sitting only a hair's breadth away in the sky, bright enough to wash out anything faint hiding nearby, unless an instrument could somehow separate the two cleanly. Neither difficulty was minor. Both required exactly the kind of technological leap that had only recently become available, and both demanded the kind of patience that, by this point in the story, the entire field had already spent 20 years cultivating. Through much of the 1970s, either approach was limited mostly to photographic plates and painstaking measurements made by hand. Methods barely changed from decades earlier, sturdy and reliable for cataloging bright stars, but poorly suited to catching something this faint. The 1980s brought real improvement, as electronic light detectors, far more sensitive than photographic film and capable of recording far fainter objects in far less time, began replacing the older methods across major observatories. Alongside them came the first dedicated infrared cameras and arrays, purpose-built to see exactly the part of the spectrum where a cool brown dwarf would do most of its glowing, technology that simply had not existed in any usable form when Kumar first did his calculations 2 decades earlier. None of this searching happened in comfortable circumstances. It happened on remote mountaintops, at observatories built specifically to sit above as much of the planet's own atmosphere as possible, where astronomers spent long, cold nights guiding a telescope by hand toward a single patch of sky, sometimes for hours at a stretch, waiting for enough faint light to accumulate on a detector to register anything at all. The air at those elevations was thin and often bitterly cold, well after dark, even in seasons that felt like summer at sea level, and the work itself was slow by nature, demanding stillness and exact aim for the sake of a single, faint smudge of light that might mean nothing at all. A single observation might require an entire night's work for what would ultimately prove to be nothing more than an ordinary star, sitting a little closer than expected. Then the astronomer would pack up before sunrise, review the results, and begin planning the next attempt on the next clear night for a target that might, once again, turn out to be nothing. Even finding a promising candidate would not have been enough on its own. The most direct way to confirm an object's mass, the single number that separates a star from a brown dwarf from a planet, is to measure how strongly its gravity tugs on something else nearby. And for an isolated object sitting alone in the dark, with nothing obviously orbiting it, that kind of measurement is often simply not available. Astronomers needed something else. A signature written into the object's own light, some detail in its spectrum that a genuine star could never produce, and that a brown dwarf, precisely because it never got hot enough to finish the job, would be forced to show. Theorists had already worked out, in principle, what a few such signatures might look like. What nobody had yet managed was catching an object bright enough, close enough, and cooperative enough to actually display one clearly, under an instrument sensitive enough to record it. Candidate after candidate turned up throughout the 1980s, Using both strategies, and one after another, they failed to hold up under closer examination. Some turned out, once properly measured, to be ordinary faint stars after all, simply sitting closer to Earth than first assumed, and therefore appearing dimmer than their true nature would suggest. Others were never definitively confirmed or ruled out at all, left hanging in a kind of scientific limbo while everyone waited for sharper instruments and better techniques to catch up with the theory. Each retraction, each unresolved candidate, added to a slowly building sense of doubt, not about the underlying mathematics, which nobody seriously questioned, but about whether these particular objects would ever actually be pinned down within any given researcher's own working lifetime. By the start of the 1990s, brown dwarfs had become something of a running frustration across the field, a mathematically sound prediction, confirmed twice over by independent calculations worked out an ocean apart, that stubbornly refused to become an actual observation. A name, in other words, for an object that still, after 15 years, belonged to no one. For the astronomers actually conducting these searches, the 2 decades between prediction and proof were not simply an abstract waiting period. Entire careers were built around the hunt, spent developing new instruments, refining search techniques, and chasing candidates that, more often than not, quietly evaporated under closer scrutiny. It is easy, from a distance of decades, to treat this as a tidy story building steadily toward its answer. It did not feel that way at the time. It felt, to the people living through it, like chasing a name that might never earn the object to go with it. By then, new tools were finally starting to catch up with the theory. Detectors sensitive to infrared light were becoming sharper, larger, and more widely available than anything researchers had access to only a decade earlier. Ground-based telescopes were being paired with these new detectors in ways that had simply not been possible before, and for the first time, a handful of research groups, working independently and often with little awareness of one another's progress, each began to suspect that the long search might finally, genuinely be within reach. Some leaned towards searching the crowded young clusters. Others kept watching for faint companions tucked in close to stars already well understood. None of them could have said with any confidence when, or which of them, or which of the 2 approaches would be the one to actually get there first. Word of each new attempt traveled quickly through a scientific community that, by this point, numbered only a few hundred people worldwide with any direct stake in the outcome. Everyone in that small community knew roughly everyone else's general approach, even without knowing the specific results anyone might already be sitting on, and a quiet, unspoken sense of urgency had settled over the whole field. Whoever found the proof first would be remembered for it, in exactly the way Kumar and Tata already were, for having asked the right question decades before anyone could answer it. It is worth noting that brown dwarfs were far from the only puzzle astronomers were racing to resolve during these same years. Across that same stretch of the early 1990s, a related and equally stubborn question sat open: whether any planet at all had ever been confirmed orbiting a normal, sun-like star anywhere beyond our own solar system. Not one had been, despite decades of searching. The 2 mysteries were not identical, but they shared a common shape. Both involved objects too faint, too close to a much brighter neighbor, or too intrinsically dim to have ever been directly confirmed, and both had become, by the early 1990s, long-standing embarrassments for a field that otherwise understood a great deal about the universe. Something was clearly about to give. Anyone working in the field by the early 1990s could have told you, if you had asked, roughly what the breakthrough would need to look like when it finally came. It would not arrive, as a single dramatic image. It would arrive as a number or a pattern buried in a spectrum, quiet and easy to miss, unless you already knew exactly what you were looking for. The kind of evidence that would mean nothing to anyone outside the field and everything to everyone inside it. Some researchers had begun to wonder, only half seriously, whether the mathematics itself might be wrong somewhere, whether these in-between objects were simply too faint, too rare, or too well hidden ever to be pinned down with the technology of the day. They were not wrong about the difficulty, they were wrong about the timeline. Within a matter of months of each other, two entirely separate research teams, working with two different telescopes on two different continents, one following each of those two search strategies, were each about to find the evidence that had eluded everyone for 2 full decades. Neither team would know, until the results were already in hand, that the other was closing in on the very same discovery at almost exactly the same time. Later in this video, we will look at exactly what each of them found and why one particular piece of evidence, hiding quietly inside a beam of ordinary light, was finally enough to settle a debate that had lasted since Kumar first put a number to the problem. 2 teams, 2 continents, 2 entirely different telescopes, watching for 2 entirely different kinds of evidence. Neither research group knew, in the early months of 1995, that the other was closing in on the same 20-year-old prediction at almost exactly the same moment. One was working from a mountaintop in the Canary Islands, off the coast of northwest Africa, watching a tightly packed cluster of young stars for any object that might be their faint, failed sibling. The other was working from a mountaintop in Southern California, watching a single, ordinary, nearby star for the faint smudge of something small enough to be hiding in its glare. Both had spent years refining exactly the kind of instrument this search required. Both were about to succeed within months of each other, using 2 completely different pieces of evidence on 2 completely different kinds of brown dwarf. And by the end of that single remarkable year, the theoretical prediction that had waited 2 decades for proof would have not 1 confirmed example, but 2. The first team worked at the Instituto de Astrofísica de Canarias, the astrophysics institute anchored on the Canary Islands, led by 3 researchers, Rafael Rebolo, Maria Rosa Zapatero Osorio, and Eduardo Martin. Their target was the Pleiades, the same young, tightly packed star cluster that had made such a natural hunting ground throughout the previous 2 decades of searching, sitting roughly 400 light-years from Earth. The observatory itself sits high on the slopes of Mount Teide, a still active volcano and the highest point in all of Spain, chosen for exactly the reason so many observatories end up on remote peaks: thin, dry, unusually still air far above the turbulence and light pollution of any city, giving a telescope the clearest possible view of anything faint enough to need it. Using the observatory's own IAC-80 telescope, the team identified a faint reddish object nestled among the cluster's brighter members, an object that behaved, in almost every visible respect, like an extremely small, extremely young, extremely dim star. The trouble was that an extremely small, dim star and a brown dwarf can look nearly identical from a distance. Brightness alone would never be enough to tell them apart. What the team needed was a single piece of evidence that only one of the 2 possibilities could produce, and they found it by turning to chemistry rather than brightness. The Instituto de Astrofísica de Canarias had built its reputation over decades as one of the premier astronomical research centers in Europe, drawing researchers from across the continent to take advantage of the Canary Islands' famously clear, stable skies. The Pleiades had been studied by astronomers and admired by ordinary skywatchers for far longer than the search for brown dwarfs had existed, star charts going back centuries included. Having a brand new, barely proven category of object turn up inside one of the most thoroughly studied, most famous patches of sky in the entire night sky was its own kind of quiet irony. The discovery that finally answered a 30-year theoretical question was found hiding inside a cluster people had been looking at with their own eyes for thousands of years. Detecting the evidence this team needed pushed the IAC-80 telescope close to its limits. The signature they were hunting for is a narrow, specific feature in a spectrum, easy to miss entirely in a noisy measurement, and easy to mistake for an artifact of the instrument itself, rather than something real coming from the object. Confirming it meant gathering enough light patiently across enough hours of observing time to be certain the signal was genuine rather than a trick of the data. The element in question was lithium, one of the lightest and most fragile elements that exists. Inside the crushing heat and pressure of a true star's core, lithium does not survive for long. Even in the smallest, coolest, dimmest true stars, the same conditions that will eventually sustain hydrogen fusion are more than enough to destroy any lithium the object was born with, burning through the entire original supply early in its life and never replacing it. A brown dwarf never reaches that threshold. Its core never gets hot enough, never gets dense enough to touch the lithium locked inside it, which meant the test was almost absurdly simple once someone thought to apply it. Look at the object's spectrum. If the lithium is gone, you are looking at a true star, however small. If the lithium is still there, fully intact, the object cannot be a star at all, regardless of how star-like it otherwise appears. Rebelo, Zapatero Osorio, and Martin found the telltale signature of lithium sitting untouched in their candidate's spectrum. The object had done everything a star does, except the one thing that defines a star, and the evidence was sitting there, preserved, exactly where a true star could never have left it. They named their discovery Teide 1, after Teide Observatory, itself named for the volcanic peak on Tenerife where it stands, and published their findings in the journal Nature that September, a venue whose name alone signaled to the rest of the scientific world that this was not another candidate destined to quietly fade from the record. Teide 1 went on to serve a role that suited it well in the years that followed, a benchmark. Because it sits inside a cluster whose age astronomers can independently measure by studying the cluster's brighter, more ordinary stars, Teide 1 gave researchers something rare, an object whose approximate age was known almost as confidently as its substellar nature, letting theorists test their cooling models against a brown dwarf of a known age, rather than having to guess at both its mass and its age simultaneously, the way most isolated brown dwarfs before and since have required. The second team worked an ocean and most of a continent away at Palomar Observatory in Southern California, part of a Caltech-led effort. Palomar occupies its own kind of remote high ground on Palomar Mountain, an observatory with a long history of major discoveries stretching back decades before this particular search began. Both institutes, on opposite sides of an ocean, had independently concluded that the only way to catch something this faint was to put the best instruments available as far from interference as geography allowed. Tadashi Nakajima led the search that first spotted the object, a faint companion sitting close to an already well-studied nearby star called Gliese 229, chosen as a target for exactly the reason nearby. Well-characterized stars made good hunting ground, close enough, at under 20 light-years away, and understood well enough already that any faint companion sitting near it stood the best possible chance of actually being caught and confirmed. One extra piece of evidence mattered enormously for this kind of search, something worth understanding on its own. A faint object sitting near a bright star in the sky might simply be sitting along the same line of sight by pure chance. Two objects at wildly different distances that happen to appear close together from Earth's particular vantage point, with no real connection between them at all. The way to rule that out is to track how each object moves across the sky over months and years. A star drifts slowly against the background of more distant stars as it travels through the galaxy, a motion astronomers call proper motion, and if a fainter object beside it is genuinely orbiting that star rather than merely sitting near it by coincidence, the two will drift together in lockstep year after year. Nakajima's team tracked exactly this kind of shared motion between Gliese 229 and its faint companion, confirming the two were gravitationally bound to one another long before any spectrum settled the question of what that companion actually was. Rebecca Oppenheimer, then a Caltech graduate student, obtained the actual spectrum of the object using instruments built partly by Keith Matthews, an instrument specialist on the team, while Srinivas Kulkarni, who held the George Ellery Hale Professorship in Astronomy and Planetary Science at Caltech, helped lead the overall effort. This second team was following the other search strategy that had defined the previous 2 decades. Rather than scanning a crowded young cluster, they were watching a single, well-understood star closely enough to catch something faint hiding in its glare. The companion they found, soon named Gliese 229b, was extraordinarily dim, exactly the kind of target that strategy had always been built to catch. But dimness alone, just as with the object in the Pleiades, could not settle the question. A very small, very old star can also be extremely dim. The team needed their own piece of unambiguous chemical evidence, and this time it came from an entirely different molecule. That molecule was methane, the same simple combination of carbon and hydrogen found drifting through the atmosphere of Jupiter, one of the most familiar gases in the outer solar system. Methane cannot survive real heat. It falls apart, breaks down into its component pieces at temperatures far lower than the surface of even the smallest true star. You will never find intact methane in a stellar atmosphere, no matter how cool and small that star might be, because a star's surface, however modest by stellar standards, still runs far too hot for the molecule to hold together. When Oppenheimer's spectrum of Gliese 229b came back, it showed something unmistakable: strong, distinct absorption bands, precisely the fingerprint methane leaves when light passes through it. A spectrum, for anyone who has never seen one, is not simply a color or a single reading. It is a graph, light broken apart by wavelength the way a prism breaks sunlight into a rainbow, with certain narrow bands of that rainbow missing or dimmed wherever a particular atom or molecule has absorbed exactly that wavelength of light on its way to the telescope. What convinced both teams, working with two entirely different objects, was the same basic kind of graph, a pattern of dips and absorption that no true star could ever produce, and that matched, with real precision, exactly what 3 decades of theory had predicted a genuine brown dwarf's light would look like once anyone finally managed to capture it. The atmosphere producing Gliese 229b's spectrum had to be running cooler than any star's atmosphere possibly could. Combined with the object's extraordinarily faint light output, the conclusion was unavoidable. Whatever this object was, it was not a star, and it never had been. The team's early estimates placed its mass somewhere in the range of 20 to 70 times the mass of Jupiter, comfortably inside the range Kumar and Hayashi and Nakano had calculated more than 3 decades earlier, and well below the threshold that would have let it ignite. That kind of spread in the estimate might sound like a problem, but it was really an honest reflection of how new this entire kind of measurement was. Nobody had ever had a real, confirmed brown dwarf to calibrate a cooling model against before. Every model in existence, up to that point, had been built entirely from theory, extrapolated forward from Kumar's original equations without a single actual object to check the math against. Gliese 229b was about to become that check, for better or worse, and the uncertainty in its exact mass would end up mattering far more than anyone realized at the time. By 1995, astronomers had grown genuinely weary of brown dwarf announcements. Enough promising candidates had quietly fallen apart under closer study over enough years that a new claim tended to be met first with caution rather than excitement. Gliese 229b broke through that caution almost immediately. When Oppenheimer's spectrum was shown to a room of fellow researchers at an astronomy conference in Florence, Italy, later that year, the methane signature was distinctive enough, unambiguous enough, that the room accepted it on sight, without the usual months of skeptical follow-up. It remains one of the rare moments in the field's history where a single spectrum, shown once, settled an argument that had run for 2 decades. That same gathering in Florence carried a second piece of history entirely on its own. In the very same conference where Gliese 229b's proof was unveiled, astronomers Michel Mayor and Didier Queloz announced their own discovery, the first confirmed planet ever found orbiting another sun-like star, a scorching giant sitting far closer to its star than Jupiter sits to our own sun. 2 separate 20-year mysteries, the reality of brown dwarfs and the reality of planets beyond our solar system, both broke open within that same conference in the same year, almost as if the universe had chosen 1995 to answer both questions. Astronomers had been asking it for a generation. Word of Tide one's confirmation, using an entirely different piece of evidence and an entirely different search strategy, arrived within that same window of months. Which of the two deserves to be called the first confirmed brown dwarf depends entirely on which question you are asking. If the question is, which object was the first ever confirmed to be free-floating, unattached to any star, sitting on its own the way most of the galaxy's brown dwarfs eventually turn out to be, the answer is Tade 1, found among the Pleiades. If the question is which object provided the first completely unambiguous spectroscopic proof, the kind that settled the argument in a single room, in a single afternoon, most historians of the field point to Gliese 229b. Neither team was trying to beat the other. Neither team even fully knew, until the results were already circulating, how close the other one had come. What both discoveries shared was more interesting than who arrived first. Each team's success traced directly back to one of the 2 search strategies that had defined the entire 2-decade hunt. The Pleiades search succeeded because a young cluster really was, just as astronomers had reasoned for 20 years, the best place to catch one of these objects still young enough and warm enough to stand out. The companion search succeeded for exactly the reason its advocates had always argued. Sometimes the best place to find something faint is right next to something bright enough to have already been studied for decades. There was something scientifically important, too, in the fact that both kinds of brown dwarf turned up in the same year, using entirely different methods. A free-floating object in a young cluster and a faint companion tucked beside an established star are, in principle, produced under different circumstances. Confirming both in such close succession told astronomers something Kumar's original mathematics had always implied, but nobody had been able to prove until that point. Brown dwarfs were not some narrow, unusual byproduct of one specific set of conditions. They were a genuine, recurring outcome of the ordinary process of star formation, showing up wherever that process played out, whether alone in a crowded stellar nursery or paired quietly beside a star already catalogued for a century. The two objects that finally proved brown dwarfs were real turned out to be strikingly different from each other, which was itself a kind of confirmation. Tidé 1, sitting in a cluster only a few tens of millions of years old, was caught relatively early in its life, likely still in or just past the brief window of deuterium fusion, warm enough that lithium alone was the clue needed to separate it from a true star. Gliese 229b told a very different story. Its spectrum showed the unmistakable fingerprint of methane, a molecule that only survives in something considerably cooler than Eventide 1, evidence of an object that had been cooling and dimming for a very long time. Its own brief deuterium fire, long since finished and forgotten. One was a young object caught near the beginning of the long, slow fade every brown dwarf eventually undergoes. The other was already deep into it. Between the two of them, in a single year, astronomers had confirmed both ends of the same long process at once. For 20 years, brown dwarf had been a name everyone in the field used and no one could point to. By the end of 1995, it was a name attached to two specific, confirmed, catalogued objects, each with its own spectrum, its own coordinates, its own place in the astronomical record. Kumar's mathematics had been right. Tata's word had found something to describe. There was a deeper significance to having two confirmed objects to study rather than one, beyond simply doubling the evidence. A single confirmed brown dwarf could always be dismissed at the margins as some kind of unusual exception, an outlier that happened to fit a theoretical description without necessarily proving the whole category behaved the way the mathematics predicted. Two confirmed brown dwarfs, found independently, using different methods in different environments, gave theorists something they had never had before, an actual pair of data points to test 3 decades of pure mathematics against. Some assumptions in Kumar's original equations and in the refinements built on top of them since held up well against the new data. Others, as the ongoing confusion over Gliese 229b's brightness would soon demonstrate, needed real revision. Theory had led observation by more than 30 years. Now, for the first time, observation had something to say back. It would have been reasonable, at that point, to assume the hardest part of the story was over. It was not. Gliese 229b carried a small, nagging problem that nobody could quite resolve, one that sat quietly in the scientific literature for the better part of 3 decades. Based on its estimated mass, the object should have been glowing more brightly than it actually appeared, not by a small margin either. Every model of how a brown dwarf of that size ought to cool and shine over time predicted more light than the telescopes were actually recording. Over the better part of 3 decades, researcher after researcher took a turn trying to explain the discrepancy. Some proposed the object might be coated in an unusually thick layer of high-altitude cloud, scattering away more light than a clear atmosphere would. Others proposed revising the cooling models themselves, arguing that brown dwarfs might simply fade faster early in their lives than the existing mathematics assumed. A few researchers wondered whether the original mass estimate had simply been too high from the start. Each explanation solved part of the puzzle and left another part standing. The cloud hypothesis could not fully account for the size of the gap. The revised cooling models created new discrepancies elsewhere, in other brown dwarfs whose brightness matched the old predictions just fine. And lowering the mass estimate created its own tension with other measurements of the system. Gliese 229b had become, without anyone quite intending it, one of the most closely studied and most stubbornly unresolved objects in the entire field, precisely because it was the one every new instrument and every new model got tested against first. The answer arrived in the fall of 2024, and it came from an international Caltech-led team using the European Southern Observatory's Very Large Telescope in Chile, and specifically two of its most advanced instruments working in tandem. One instrument, called Gravity, was sensitive enough to do something no earlier telescope pointed at this object had ever managed. It split what had always appeared to be a single point of light into two separate, distinct bodies. Gravity achieves that extraordinary sharpness by combining light from several of the Very Large Telescope's separate mirrors at once, effectively letting them work together as a single telescope, far larger than any one of them alone, a technique capable of picking out details no single mirror, however large, could resolve by itself. The other instrument, called Cryas Plus, measured the motion of molecules in each of those two bodies' atmospheres closely enough to confirm they were genuinely orbiting one another, rather than simply sitting near each other by chance alignment. For nearly 30 years, every telescope pointed at Gliese 229b had returned the same simple result, one point of light. However, that light was measured, or however many times the measurement was repeated. The Very Large Telescope's resolution was the first fine enough to ask whether that single point of light was hiding something. It was. Gliese 229b, the very first brown dwarf ever confirmed, the object that broke a 20-year drought in a single afternoon in Florence, was not one brown dwarf at all. It was two, locked in a tight orbit around each other, completing a full circuit every 12 days, separated by a distance only about 16 times the gap between the Earth and our own moon. Picture what an orbit like that actually means. Our own moon takes a little over 27 days to complete one circuit around Earth, at a distance of about 238,000 miles. Gliese 229 bar and BB, each one dozens of times more massive than the planet Jupiter, complete an entire orbit around each other in less than half that time, separated by a gap only 16 times as wide as the one between Earth and its moon. Two objects, each far more massive than anything in our solar system besides the Sun itself, swinging around a shared center of gravity at a pace and a closeness that would be almost unthinkable for two planets, let alone two objects this large. Astronomers now call them Gliese 229ba and Gliese 229bb, with masses of roughly 38 and 34 times the mass of Jupiter. Added together, their combined light matched, almost exactly, what the old single-object models had always struggled to explain. Two smaller, dimmer objects, sharing the light between them, had been hiding inside the glow of what everyone had assumed for 29 years was only one. The pair, in turn, orbits their distant parent star, Gliese 229a, once every 250 years. Among the co-authors of the 2024 study confirming the discovery was Rebecca Oppenheimer, the same researcher who, as a graduate student nearly 30 years earlier, had captured the original spectrum that first proved Gliese 229b was a brown dwarf at all. She had spent the better part of a career watching this particular object, present at its introduction and present again when it finally explained itself. Few scientists get to watch a single discovery unfold across the full arc of their own working life. From a young researcher's first confirming spectrum to a senior astrophysicist's role in solving the very puzzle her own early work had helped create. The mystery had waited 29 years for an instrument sensitive enough to answer it. It is a fitting, quiet detail that one of the people finally answering it had also been there at Palomar the night it first began. In the years between its first confirmation and its recent unmasking as a pair, Gliese 229b became the subject of hundreds of separate research papers, more scrutiny than almost any other object of its kind has ever received, which made the fact that it kept its central secret for so long all the more remarkable. The correction rippled outward in ways that went beyond a single object's biography. For 29 years, every population study, every statistical survey of how brown dwarfs are distributed by mass, every estimate of how common an object of roughly 70 Jupiter masses actually is, had counted Gliese 229b as one single object of that size. It never was. It was always two objects, each closer to Jupiter's own mass multiplied by 35 or so, and every one of those statistical surveys now needed, at minimum, a footnote and in some cases a genuine correction. A single object turning out to be a pair does not just change what we know about that object. It quietly reaches backward and touches every broader conclusion that object was ever used to help support. The discovery also raised a question that reached well beyond this one object. If the very first brown dwarf ever confirmed, studied more closely, and for longer than almost any other object in the field, could hide a companion for 29 years, an uncomfortable possibility followed. How many of the thousands of other brown dwarfs catalogued since 1995, each one studied far less closely than this particular founding example, might be quietly hiding the same kind of secret? Nobody had an answer. It was, itself, a fitting reminder that confirming an object exists and fully understanding what it actually is are two very different accomplishments, separated in this case by 29 years and a telescope that would not exist until long after the original discovery was made. Added up, and the full arc from Kumar's first calculation to this particular resolution spans more than 60 years, a theoretical prediction in the early 1960s, a working name in 1975, confirmed proof in 1995, and a wholly unexpected final twist in its own founding object in 2024. Few scientific stories move in a single straight line from idea to closed case. This one had already taken 4 distinct leaps across 6 decades, and it was still not finished. The years immediately following 1995 looked very different from the 2 decades that preceded them. Astronomers no longer had to search blind, hoping to recognize a brown dwarf signature without ever having seen a confirmed example to compare against. They now had 2 real spectra, 2 real sets of measurements, 2 genuine templates for exactly what to look for. Large-scale sky surveys designed to scan enormous swaths of the sky in infrared light, tools like the 2-micron All-Sky Survey and the Sloan Digital Sky Survey began turning up confirmed brown dwarf after confirmed brown dwarf throughout the second half of the 1990s, each one sharing the same telltale methane signature that had first appeared in Gliese 229b's spectrum. Astronomers had gone, within the space of only a few years, from possessing 0 confirmed examples of an entire predicted category of object to possessing dozens and then hundreds. A brand new letter, T, was eventually added to the traditional system used for classifying stars by temperature, a scheme that had gone unchanged for more than a century, specifically to make room for objects like Gliese 229b, too cool, and too fundamentally different from any true star to fit anywhere in the existing scheme. For the researchers on both teams, the moment of confirmation carried a weight that a research paper's dry language rarely captures. For Oppenheimer, watching that first faint companion resolve into an actual, confirmed object smaller than any star, genuinely orbiting another distant sun, ranked among the most exhilarating moments of her career, by her own account years later. It is worth remembering what these researchers had actually been chasing, not a new planet, of which a handful had already been glimpsed indirectly by that point. Not simply a new kind of star, of which thousands of varieties were already catalogued. Something in between, something with no confirmed precedent anywhere in the historical record, a genuinely new kind of object that had existed on paper for 2 decades without a single real example to point to. Both teams got to be among the first people ever to look at hard evidence and know, with real confidence, that the category was real. By the end of 1995, the 20-year theoretical drought was over, and brown dwarfs had gone from a name in search of an object to 2 confirmed examples with spectra, coordinates, and research papers attached to their names. By the end of 2024, even the very first of those 2 confirmed examples had turned out to be more complicated and more interesting than anyone in that room in Florence could have known. Both discoveries answered the same basic question: are these objects real? Neither one answered a much larger set of questions that remained completely untouched. What does a brown dwarf actually look like up close, if there were such a thing as up close? What does its surface do, hour to hour, day to day? Does anything happen on a world with no sun of its own to warm it? Those questions would take another kind of evidence entirely, and another generation of telescopes to begin to answer. Up close, as it turns out, is a genuinely strange place to stand. A brown dwarf is not a point of light or a spectrum on a graph. It is a physical world roughly the size of Jupiter, wrapped in moving bands of cloud, spinning fast enough to finish a full day in a matter of hours, and in at least one confirmed case, lit up by an aurora so powerful it would put anything in our own solar system to shame. None of this was visible in 1995. Confirming that brown dwarfs existed had taken lithium, methane, and 2 decades of patient searching. Understanding what they were actually like once they had been found would take a different kind of patience entirely, and a different set of tools. Start with something almost nobody expects the first time they hear it. Take a brown dwarf sitting near the bottom of its mass range, something around 15 times the mass of Jupiter, and compare it to one sitting near the very top, closer to 75 times the mass of Jupiter. You would expect the heavier object to be dramatically larger. It is not. Both objects come out to almost exactly the same size, roughly the width of Jupiter itself, give or take a small margin. Piling on nearly 5 times the mass barely changes the diameter at all. The reason comes down to what happens to matter once you compress it past a certain point. In an ordinary gas, adding more material and more gravity makes an object bigger, the way adding more air to a balloon makes the balloon expand. Once matter gets crushed dense enough, though, a different rule takes over, called electron degeneracy pressure, a kind of resistance to further compression that has nothing to do with heat or ordinary gas pressure. Past that threshold, adding more mass no longer makes the object meaningfully bigger, it only makes it denser, the extra weight packed into essentially the same volume rather than expanding outward. A star avoids this fate because its own fusion furnace generates enough outward heat and pressure to keep ordinary gas physics in charge, letting more massive stars grow larger, not just denser. A brown dwarf never lights that furnace, or lights only a brief, weak version of it, so degeneracy pressure takes over almost from the start and stays in charge for the rest of the object's existence. This same basic principle, matter reaching a point where it resists further compression, regardless of temperature, is the same one that holds up a white dwarf, the very object whose name Kumar's theoretical objects were not allowed to borrow, all the way back at the beginning of this story. A brown dwarf and a white dwarf are, in this one specific sense, close cousins, both supported against total collapse by degenerate matter rather than by fusion. The difference is what lies inside each one. A white dwarf is the leftover core of something that spent billions of years successfully burning through its nuclear fuel first. A brown dwarf never got that chance. Both end up, eventually, doing the same quiet thing, sitting in the dark, slowly radiating away whatever heat remains, asking nothing further of the universe around them. This creates a genuine headache for anyone trying to study an individual brown dwarf from a distance. Size alone cannot tell you the mass, since a young lower mass object and an older higher mass object can appear almost identical in size, and because both are simply cooling over time, sometimes in brightness as well. A given brightness might belong to a young, small brown dwarf that has not had time to cool much yet, or to an old, more massive one that has been cooling for billions of years and has faded to match. Untangling the two usually requires some independent way of estimating age, the way a cluster's well-studied stars can pin down the age of a member like Tidy One. An isolated brown dwarf, floating alone with no such neighbors, often keeps that particular secret to itself. The clouds themselves are not made of water vapor the way clouds on Earth are, at least not in the warmer members of the category. In the hotter brown dwarfs, closer to the top of the mass range and still carrying real leftover heat from their formation, the condensing material is something closer to what forms inside a furnace than what forms in an ordinary sky. Droplets of iron and grains of silicate minerals, the same rocky material that makes up most of Earth's crust, condensing directly out of an atmosphere hot enough to vaporize rock in the first place. Cool the object down further, and the chemistry shifts again, iron and silicate giving way to compounds like sulfide salts, and, at the very coldest extreme, water and ammonia ice. A brown dwarf's clouds are not a fixed feature. They are a kind of thermometer, the composition itself changing as the object cools, decade after decade, through an entire sequence of different sky. The blistering rotation speeds involved are not an accident either, and they connect to something people who watched figure skating on television for decades already understand intuitively. A skater pulling their arms in tight spins faster than the same skater with arms spread wide, the same total spin preserved but concentrated into a smaller shape. A collapsing cloud of gas and dust behaves the same way. Whatever slow, gentle rotation that cloud carried at the very start, spread out across trillions of miles, gets preserved as the cloud collapses down into an object barely wider than Jupiter, and concentrating that same rotation into a vastly smaller size means it has to spin dramatically faster to conserve it. A star undergoes the same basic process, but a star's rotation gets slowed over billions of years by its own stellar wind and magnetic field, gradually bleeding away angular momentum into space. A brown dwarf, lacking any real stellar wind of its own, never gets that same brake applied. Whatever fast spin it was born with tends to stay close to what it started with, for as long as the object exists. For a close, detailed look at exactly this kind of weather, astronomers did not have to look very far. In 2013, an astronomer named Kevin Luhman identified a pair of brown dwarfs orbiting each other at a distance of only about 6.5 light years from our own Sun, making it, at the time of its discovery, the closest brown dwarf system ever found, and still the closest one known today, trailing only the Alpha Centauri system and Barnard's star among all of our nearest stellar neighbors. The pair, now known simply as Luhman 16, consists of two brown dwarfs orbiting each other roughly every 25 years at a separation of about 3 astronomical units, a little further apart than Earth sits from our own Sun. One component runs slightly warmer, classified in the L category of brown dwarf types. The other runs cooler, classified in the T category, sitting close to the dividing line between the two. The L and T labels are part of a classification system astronomers extended specifically to make room for objects like these, picking up where the traditional star classification scheme leaves off. Ordinary stars run through a sequence of letters organized by temperature, hottest to coolest. Brown dwarfs continue that same sequence into territory no true star ever reaches. L for the warmer end of the category, glowing a deep red and patterned with iron and silicate clouds. T for the cooler methane-bearing objects like Gliese 229b, and, cooler still, a final category called Y, reserved for the most extreme objects on record, some of them cool enough to approach room temperature. Luhman 16, with one component of each of the two warmer types sitting side by side in a single system, offered astronomers something close to a laboratory. Two different stages of the same long cooling process, at the same distance, studied with the same instruments, at the same time. The cooler of the two components, called Luhman 16b, became the first brown dwarf ever mapped in real detail. Astronomers tracked its light as it rotated once every 4.9 hours by one measurement, fast enough to complete an entire day faster than Earth completes a single afternoon. As the object spun, its brightness rose and fell in a repeating pattern, and researchers used a technique called Doppler imaging, tracking tiny shifts in the object's light caused by different patches of its surface moving toward or away from Earth at slightly different speeds as it rotates, to reconstruct an actual, if rough, map of what was moving across its face. What they found were bands of cloud, patchy and uneven, drifting and evolving as the object turned, not unlike the storm bands astronomers have long tracked on Jupiter itself, except here. The entire signal was coming from an object with no sunlight of its own to illuminate it, glowing and shifting purely by its own residual heat, capturing a reliable light curve, a precise record of exactly how an object's brightness rises and falls over the course of its rotation, is not a single quick observation. It requires watching the same object, continuously or in a tight sequence, for at least one full rotation and usually many more, to separate a genuine repeating pattern from ordinary noise or a one-time fluctuation. For an object rotating in under 5 hours, that meant staying trained on Luhman 16b for the better part of a night, watching the pattern repeat itself again and again to be sure it was real. Space-based telescopes proved especially valuable for this particular kind of work, since they avoid the flickering distortion Earth's own atmosphere adds to any observation taken from the ground, a distortion that becomes especially troublesome when trying to measure a brightness change of only a few percent from one moment to the next. Follow-up studies found the brightness variation on Luhman 16b to be substantial, swinging by more than 10% over the course of a single rotation in some measurements. Evidence not simply of clear patches alternating with cloudy ones, but of multiple layers of cloud at different heights and different thicknesses, drifting past each other at different rates, the way separate weather systems on Earth can overlap and interact rather than moving as one uniform blanket. This was not a static, frozen world. It was an active one, its visible face genuinely changing, storm system by storm system, on a timescale of hours rather than centuries. Watching a single rotation only tells part of the story. Astronomers who return to Lumen 16b and similar objects night after night, tracking the same cloud features across many rotations spread over weeks and months, found that some patterns persisted stubbornly, reappearing rotation after rotation in roughly the same location, while others shifted, merged, or vanished entirely within only a handful of days. It is a pattern with at least a loose echo close to home. Jupiter's own Great Red Spot has churned in roughly the same place for centuries, while countless smaller, less durable storms have flared up and faded away around it within a single human lifetime. Brown dwarfs, it turns out, may host both kinds of weather at once, some features built to last, others built to pass. Lumen 16b was an especially favorable case, close enough and bright enough to study in this kind of detail with the instruments available at the time. In the years since, space telescopes built specifically for infrared work, first Spitzer, then increasingly the James Webb Space Telescope, have extended this same kind of light curve monitoring to dozens of other brown dwarfs across the L, T, and Y classes, tracking how common-banded, patchy, evolving clouds actually are across the category as a whole, rather than relying on one especially convenient nearby example. The emerging picture suggests that some degree of cloud variability may be close to universal among brown dwarfs, at least at certain temperatures and certain stages of the cooling process, though the details, how patchy, how fast changing, how deep beneath the visible surface, continue to vary enormously from one object to the next. The system had one more twist worth mentioning. In 2017, a subtle wobble detected in one of the two brown dwarfs suggested it might have a planet of its own in orbit, roughly the mass of Neptune, a genuinely tantalizing possibility. A planet orbiting not a star, but a brown dwarf barely larger than Jupiter itself. A confirmed planet like that would have mattered for reasons beyond novelty. It would have offered a working example of planet formation happening around an object that itself only barely avoided being a star, and would have raised genuine questions about what kind of world could form and survive orbiting a parent that generates almost no light or warmth of its own. Additional observations and a more careful reanalysis of the data in the years that followed failed to confirm the signal, and the candidate planet was ultimately ruled out. The false alarm did not resolve any of those questions. It simply left them exactly where they had been before anyone thought they had found an answer, and it stands as a useful reminder that not every promising signal survives a second look. A year after identifying Lumen 16, the same astronomer, Kevin Lumen, found something even stranger: the coldest brown dwarf ever confirmed, and for years afterward, the coldest one still on record. It is worth pausing on the fact that one astronomer, working only a year apart, delivered both the closest known brown dwarf system and the coldest known brown dwarf on record. Kevin Lumen's name would go on to reappear throughout the following decade of brown dwarf research, credited again and again in survey after survey, a reminder that a field this young, barely 50 years removed from Kumar's original mathematics at the time of Lumen's two discoveries, still had room for a single researcher's careful, patient survey work to reshape the record books twice within the same short stretch of years. He spotted this second object in 2014 by comparing images taken months apart by an infrared survey satellite, watching for anything that appeared to crawl slowly across the sky relative to the background of more distant stars. The telltale sign of an object close enough to us that its own motion through space becomes detectable. The object, catalogued as Y0855-0714, sits at a distance of a little over 7 light-years, making it one of the closest known systems to our own Sun, and yet it had gone completely unnoticed until that point, for a simple reason. It was almost unbelievably cold. Just how cold is worth sitting with for a moment. The best current estimates put its temperature somewhere in the neighborhood of 10 degrees below 0 Fahrenheit, depending on which atmospheric model is used, cold enough that, if you could somehow stand on its surface, the temperature would feel closer to a brutal winter night in the northern United States than to anything resembling a star. This is a brown dwarf so thoroughly finished with its own brief burst of youthful fusion, so many billions of years into its long cooling process, that it has faded almost entirely out of the range where earlier infrared surveys could have found it at all. Every brown dwarf eventually heads in this direction. WISE 0855-0714 simply shows what waits at the far end of that road, decades or eons ahead of where Tidy 1 and Gliese 229b still sit. At temperatures this low, something else becomes possible that has never been confirmed anywhere else among brown dwarfs. Actual water ice, condensing directly out of the atmosphere the way frost forms on a cold window. Some early modeling of WISE 0855's light supported this picture, water clouds genuinely forming in its upper atmosphere. Later studies were less certain, some finding no clear evidence of water clouds at all, and a study using a powerful new space telescope in 2025 found less water present in the upper atmosphere than earlier models had predicted, deepening the uncertainty rather than resolving it. WISE 0855 sits so far down the cooling sequence that it strains even the Y classification created to describe the coldest known objects, and beyond the debate over water, its spectrum has also been examined for other telltale cold weather chemistry. Ammonia, among it, the kind of ice and condensate that never appears in warmer brown dwarfs, simply because it is too hot there for it to form or survive. Untangling exactly which compounds are present and in what quantities requires separating an extraordinarily faint signal from instrument noise, since this remains one of the faintest objects ever directly studied by any telescope on Earth or in orbit around it. The honest state of the science, at least for now, is that nobody has definitively confirmed water clouds on any brown dwarf, including this one, even though the temperature would allow for them in principle. Because it sits so close and so far down the cooling sequence, WISE 0855-0714 has become something of a proving ground in its own right, the object researchers return to whenever a new instrument or a new atmospheric model needs to be tested against the coldest conditions actually known to exist outside a laboratory. The 2025 findings on its water content came from exactly this kind of return visit, a newer, more sensitive telescope checking an old, well-studied target, and finding the picture was not quite as settled as earlier instruments had suggested. There is a further wrinkle specific to this particular object. Some mass estimates for WISE 0855-0714 run as low as 3 to 10 times the mass of Jupiter, which, if accurate, would place it below even the lower deuterium fusion threshold established decades earlier by Kumar and Hayashi and Nakano. An object that light would never have fused anything at all, not even briefly, making it technically a free-floating planet rather than a true brown dwarf by the strictest definition of the category. The coldest object of its kind on record may not, by some measurements, actually belong to the category it is famous for representing, a fitting complication for a field where the boundary between planet and brown dwarf has never been as clean as the mass numbers alone suggest. Weather and temperature are not the only signs of an active world. In 2006, a graduate student named Greg Hallinan discovered something nobody expected from an object with no fusion furnace and no stellar wind. Brown dwarfs pulse at radio frequencies in a pattern remarkably similar to the radio pulses generated by the auroras of planets in our own solar system. It was a strange finding on its own. It would turn out to be the beginning of a much bigger one. Jupiter's own aurora, driven by the planet's powerful magnetic field and fed partly by volcanic material streaming off its moon, Io, already ranks as the most intense aurora anywhere in our solar system, visible, even in ultraviolet light, captured by orbiting telescopes, far outshining anything ever seen dancing above Earth's own poles. It was against this benchmark, the single most powerful aurora already known anywhere nearby, that Hallinan's team would soon measure something even more extreme. 9 years after his first discovery, by then a professor at the California Institute of Technology, Hallinan led a team studying a brown dwarf called LSR J1835 plus 3259, sitting about 20 light-years from Earth. Using the National Radio Astronomy Observatory's Very Large Array in New Mexico, the Keck Observatory's telescopes in Hawaii, and the historic Hale Telescope at Palomar, the same observatory that had produced Gliese 229b 2 decades earlier, the team confirmed something remarkable. Coordinating 3 separate observatories for a single target is not simple logistics. The radio data from the Very Large Array told the team an aurora-like pulse was present and let them measure its strength. The infrared and optical observations from Keck and from Palomar were what let them confirm, beyond doubt, exactly which object in the sky that pulse was coming from, and pin down its basic properties well enough to rule out any other explanation. Radio waves alone can reveal that something remarkable is happening. They cannot, on their own, tell you what kind of object is doing it. That confirmation still requires seeing the object itself in the more familiar wavelengths every earlier brown dwarf discovery in this story had also depended on. The object was generating an aurora, and not a modest one. By the team's measurements, it was hundreds of thousands of times more powerful than any aurora ever recorded anywhere in our own solar system, dwarfing even the most intense auroral storms ever observed on Jupiter, emanating from an object with no planetary system of comparable scale, and by every available measurement, no star anywhere nearby feeding it the particles it would need to shine that way. On Earth, and on every other planet in our solar system with an aurora, the mechanism is well understood. Charged particles streaming out from the sun, caught and funneled by a planet's magnetic field down toward its poles, colliding with the upper atmosphere and lighting it up. A brown dwarf has no nearby star supplying that stream of particles. It generates no solar wind of its own to speak of. Whatever is powering an aurora this intense has to be coming from somewhere else entirely, and years after the discovery, nobody has definitively identified what that source is. One proposed explanation involves an unseen planet or smaller companion orbiting close enough to the brown dwarf to interact with its magnetic field, generating an electrical current, the way the moon Io generates one within Jupiter's own magnetosphere. Nobody has confirmed such a companion exists around this particular object. The aurora remains real, repeatedly observed, and genuinely unexplained. Magnetic fields, this strong, were not something theorists had confidently predicted before Hallinan radio detections started coming in. A brown dwarf generates its magnetic field through motion deep in its interior, churning convection carrying heat outward from its slowly cooling core, a process related to, but distinct from, the mechanism that generates Earth's own much weaker field. What surprised researchers was how strong that field could get on some brown dwarfs, rivaling or exceeding the fields measured on some genuine stars, despite the complete absence of the fusion-driven processes assumed to be necessary for a field that powerful. Brown dwarfs, it turned out, did not need to be stars to generate star-strength magnetism. Later radio surveys turned up auroral activity on several other brown dwarfs beyond LSR J 1835 plus 3259, spanning a range of the L and T classes, suggesting powerful magnetic fields and unexplained auroras may be a genuinely common feature of the category, rather than one strange exception. The mystery was not confined to a single unusual object. It appeared to be a basic property of brown dwarfs as a class, one that just happened to be discovered first on the one object bright enough, in radio waves, to be caught early. One particular signature makes an auroral radio signal recognizable as exactly that, rather than simply background noise or an unrelated source. Circular polarization, a specific twist to the radio waves themselves, produced when charged particles spiral along magnetic field lines in the particular way an aurora requires. Spotting that twist in a signal is how Hallinan's team confirmed they were looking at a genuine magnetic aurora and not some other unrelated kind of radio noise entirely, and the same signature would prove essential for what came next. The discovery of a radio-loud aurora on a known brown dwarf raised an obvious follow-up question. Could an entirely new brown dwarf be found this way through its radio emission alone, before anyone ever spotted it in infrared light at all? In 2020, a team using a radio telescope array, called LOFAR, spread across sites in Europe, answered that question directly. They detected a circularly polarized radio source that infrared surveys had never flagged as anything unusual, and follow-up observations confirmed it was a genuine brown dwarf, a cold methane-bearing object sitting roughly 200 light-years away. It was the first brown dwarf in history to be discovered by its radio emission before its infrared signature, an entirely new front door into a category of object that had, until that point, only ever been found by searching for faint heat. The discovery team gave the object an informal name, Elegast, borrowed from a dwarf-like spirit in a centuries-old Middle Dutch poem, a small, human touch on an object that had just expanded the entire toolkit available for finding objects like it. LOFAR itself is not a single dish but a network. Thousands of simple radio antennas spread across sites in the Netherlands and several neighboring countries, all linked together and combined electronically to work as one enormous distributed radio telescope. That design makes it especially well suited to scanning wide swaths of sky at low radio frequencies, exactly the kind of broad, patient search that eventually turned up Elegast's signal among the noise. Every brown dwarf, found through infrared light, depends on that object still being warm enough to glow, faintly, in wavelengths a telescope can register. The coldest, oldest, most thoroughly faded brown dwarfs, the ones that have had the most time to cool toward the very bottom of the category's long, slow decline, are exactly the ones infrared surveys are most likely to miss entirely. A radio search does not share that limitation. In the same way, the implications reach further than brown dwarfs alone. If a radio search can catch an object too cold and too faint for infrared surveys to notice, the same basic method might eventually be turned toward objects smaller still, free-floating planets with no star of their own, radiating so little heat that no infrared telescope built so far could ever hope to register them directly. Nobody has confirmed such a detection yet, but the existence of Elagast proved the underlying principle works, and proved it using a technique nobody had thought to seriously apply to this particular puzzle before 2020. Taken together, these discoveries marked a genuine shift in what it meant to study a brown dwarf. The work of 1995 had been about proving a category of object existed at all. The work of the years that followed, mapping Lumen 16b's clouds, measuring WISE 0855's cold, chasing the source of an aurora nobody could explain, listening for objects too faint for any telescope built to see heat, was about something different. Treating each confirmed brown dwarf not as a data point confirming a theory, but as an individual world with its own weather, its own history, and its own unanswered questions. None of this vivid detail had come cheaply or quickly. Each discovery, the cloud map, the cold record, the aurora, the radio first detection, had required its own dedicated instrument, its own patient observing campaign, sometimes its own decade of waiting for the right technology to catch up with the question being asked. And even after all of it, the population of brown dwarfs known well enough to study this closely remained a small fraction of however many were actually out there, scattered through the galaxy, most of them fainter, colder, and farther away than any object described so far. Between the cloud bands mapped on Lumen 16b, the water ice possibly condensing in the frozen atmosphere of WISE 0855, and an aurora with no confirmed source, lighting up the sky of an object with no sun, brown dwarfs had, by any honest measure, stopped looking like simple cosmic leftovers. They were active, weathered, individually distinct worlds, each one behaving differently depending on its exact mass, its exact age, and its exact history. And yet, for all of that vivid, hard-won detail, the most basic question of all, where exactly a brown dwarf stops being a very large planet and where it stops being a very small star, remained stubbornly unsettled. The mass numbers that had seemed so clean at the very beginning of this story, 13 Jupiter masses on one side, 80 on the other, were about to look considerably less tidy. Less tidy is putting it kindly. Two of the most closely watched puzzles in the entire field, one about where brown dwarfs are found, and one about whether an entire class of them exists at all, remained genuinely, publicly unresolved, even as this very episode was being put together. And a discovery announced only months ago revealed that the map of how many of these objects exist had been wrong, not by a small margin, but by roughly half. Start with the desert itself, a name astronomers gave to a genuinely strange gap in the data. Point a sensitive enough instrument at a sun-like star and search for close companions, objects orbiting within a distance of only a few times the gap between Earth and our own sun, and planets turn up at a reasonable rate, something in the neighborhood of 5 or 6 stars out of every 100. Search that same close orbit for full, ordinary stellar companions, and you find them at an even higher rate, something closer to 10 or 15 out of every 100. Search for a brown dwarf sitting squarely in the mass range between those two categories in that same close orbit, and the rate collapses to less than 1 star in 100. Objects that should, by simple logic, be intermediate in abundance the way they are intermediate in mass, turn out to be almost entirely missing from exactly the orbits astronomers expected to find them. The gap was first noticed in radial velocity surveys during the late 1980s and early 1990s, the same general era and often the same instruments that were closing in on the first confirmed brown dwarfs themselves. The radial velocity method that first revealed the desert works by watching a star's own light for an extremely subtle, rhythmic shift, evidence that the star itself is being tugged ever so slightly back and forth by the gravity of something orbiting it, even when that something is far too faint to see directly. A star with a heavy, close companion wobbles more noticeably than a star with a light one, which is exactly what makes the method so good at finding brown dwarfs in principle. Since brown dwarfs sit heavier than any planet, that same sensitivity is what made their near-total absence in close orbits so hard to dismiss as some kind of oversight. The method was more than capable of finding them. It simply kept finding almost none. Astronomers gave this gap a name that stuck immediately: the brown dwarf desert. The name captures the shape of the problem better than any careful scientific description could. Nothing about the underlying physics obviously predicts this gap. A brown dwarf forming in a close orbit around a young star should, in principle, be a perfectly reasonable outcome of the same basic collapse process that builds planets and stars throughout that same system. And yet, in survey after survey, spanning multiple independent research groups working with different instruments over several decades, the gap kept showing up, stubborn and consistent, exactly where the mathematics offered no obvious reason for one to exist. The strangest part of the desert is how narrow it actually is. Move a brown dwarf companion out to a much wider orbit, hundreds or even 1,000 times farther from its star than the desert's inner boundary, and the scarcity disappears almost entirely. At those wider distances, brown dwarf companions turn up at rates far closer to what simple logic would predict, comfortably common, no longer avoiding their host stars at all. Whatever mechanism is responsible for the desert, it appears to operate specifically, almost surgically, on close-in orbits, and to lose its grip entirely once a brown dwarf gets far enough away. The desert, in other words, is not a statement about brown dwarfs in general. It is a statement about brown dwarfs standing too close to a star for their own gravitational good. Several explanations have been proposed for the close-in scarcity itself, and none of them has managed to fully close the case. One holds that a close-in brown dwarf slowly loses energy to the gravitational pull of its host star, spiraling inward over millions of years until it is eventually swallowed whole, meaning the desert is not empty so much as it is a graveyard, its former residents long since consumed. Another holds that young brown dwarfs get ejected from these systems entirely, flung outward or away by gravitational interactions with other objects still forming nearby, scattered into the free-floating population that turns out to be common everywhere except in these close, inner orbits. A third holds that the disk of material surrounding a young star simply favors building either much smaller planets or much larger stellar companions, with the brown dwarf mass range sitting in an awkward, disfavored middle that the disk itself tends to skip over. Each explanation accounts for part of the pattern. None of them, on its own, accounts for all of it. And now there is a further complication, one that only became clear very recently, using data from the Gaia Space Telescope, a mission built to measure the positions and motions of well over 1 billion stars with extraordinary precision. Earlier desert surveys, relying mainly on that same telltale wobble, could measure how strongly an object tugged on its star, but could not always tell how that tug was oriented in three-dimensional space. An ambiguity that can make a companion's true mass look smaller or larger than it actually is. Combining those older measurements with Gaia's precise astrometry removes much of that ambiguity, and when researchers did exactly that, several objects long counted as members of the brown dwarf desert turned out, on closer inspection, to actually be low-mass stars, misclassified for years by a measurement uncertainty nobody could fully resolve until an instrument sensitive enough came along. That single correction does not erase the desert entirely. Even accounting for it, close-in brown dwarf companions remain genuinely rare. But it does something almost as interesting. It suggests the desert may be less like a fixed absolute gap sitting between 13 and 80 Jupiter masses, and more like a relative one, its exact boundaries shifting depending on the mass of the star being orbited. There is a newer way of describing this that some researchers now find more useful than counting in raw Jupiter masses at all. Instead of asking how many companions fall between 13 and 80 times the mass of Jupiter, this approach asks what fraction of the host star's own mass the companion represents, a ratio rather than an absolute figure. Measured this way, the gap shows up as a dip somewhere around 2 to 5 companion masses for every 100 units of the star's own mass, a pattern that holds up remarkably well whether the host star is considerably lighter than our own sun or considerably heavier. That consistency is itself telling. It suggests the underlying cause has less to do with any single fixed mass in Jupiter units and more to do with some proportional relationship between a forming disk and the star at its center. A companion that would count as a brown dwarf next to a star like our own sun might fall on the stellar side of the line next to a smaller, lighter star, and on the planetary side of the line next to a larger, heavier one. The desert, in other words, may not be a fixed region on a map at all. It may be a boundary that moves depending on where you are standing when you draw it. A very different kind of boundary trouble showed up in an entirely different corner of the sky, in the Orion Nebula, a vast stellar nursery roughly 1,300 light-years from Earth, and one of the most productive star-forming regions astronomers have ever studied. Late in 2022, using the James Webb Space Telescope, two astronomers, Mark Makorian and Samuel Pearson, surveyed a small patch of the nebula's crowded central region. The survey itself was a substantial undertaking, roughly 35 hours with the telescope's near-infrared camera trained on a single patch of sky a little over a parsec across, using a dozen different filters specifically chosen to pick out the faint chemical fingerprints, water and methane among them, that separate a genuine young substellar object from an ordinary background star. Out of that survey came several hundred candidate planetary mass objects scattered among the nebula's young stars, most of them sitting alone. A striking fraction, roughly 1 in 10, appeared to be sitting in pairs, two planetary mass objects orbiting a shared center of gravity, unattached to any star at all. The team gave these paired objects an informal name of their own, Jupiter Mass Binary Objects, nicknamed Jumbos, and the discovery, announced in 2023, immediately posed a serious problem for existing theory. Nothing in the accepted models of how stars and planets form offers a clean explanation for how two objects this small, some barely more massive than Jupiter itself, could end up gravitationally bound to each other, orbiting at distances far too wide for standard formation theory to comfortably explain, with no parent star anywhere nearby to have shepherded them into that arrangement. If real, The jumbos would mean nature can somehow assemble genuine binary systems out of almost nothing but a pair of planet-sized objects and empty space, a result that would force real revisions to how astronomers think planetary systems come together in the first place. The complication came a year later. In 2024, the astronomer Kevin Luhman, the same researcher who had identified both Luhman 16 and WISE 0855 earlier in this story, went back through the original survey data with a more careful eye. His method involved comparing each candidate's color, essentially how its brightness differs between different infrared wavelengths, against the well-established color signatures of confirmed young brown dwarfs in similar star-forming regions. A genuine young, nearby substellar object has a fairly distinctive signature. A distant, reddened background star, its light scattered and dimmed by dust along the way, can mimic parts of that signature closely enough to fool a first look, but tends to diverge from it in ways a careful, systematic comparison can catch. Running the full catalogue of candidate pairs through exactly that comparison was what allowed Luhman to separate the handful of genuinely promising cases from the majority that, on closer inspection, no longer looked so convincing. The great majority of the candidate jumbo pairs, checked this way, looked instead like something far less exotic: reddened background stars sitting thousands of light years further away, whose light happened to pass through enough dust to mimic the appearance of something young and faint and close. Of the original candidates, Luhman found only a single pair that still held up as a plausible, genuine binary system. The rest, by his analysis, were very likely an illusion built from contamination, not a new class of object at all. The stakes of the dispute reach beyond a single nebula. If even a handful of genuine jumbos survive close scrutiny, astronomers will need to seriously reconsider how loosely bound planet mass pairs can form in the first place, since no existing model comfortably explains it. If Luhman's skepticism holds up instead, and the vast majority turn out to be background contamination, the lesson is a different but equally important one: that even the most rigorous-looking survey, using the most advanced telescope ever built, can be fooled by a dusty coincidence dressed up to look like something new, and that verifying an extraordinary discovery can take longer and require more independent scrutiny than making the initial claim ever did. The disputed jumbos sit inside a broader, equally unsettled question about objects with no star at all. Free-floating planets, wandering the galaxy unattached to anything, some of them possibly ejected from systems that once held them, others perhaps forming on their own from the start, the same way a star forms, only falling short of even the lower brown dwarf threshold. This hour has already brushed against exactly this ambiguity once, in an object cold enough that its own mass estimate dips low enough to raise the same question. Wherever the true edge of the brown dwarf category sits, it appears to fade rather than snap into place. Planets shading into brown dwarfs, shading into stars, along one long, continuous scale, with astronomers doing their best, generation after generation, to mark off sections of it with names. The dispute has not been fully settled either way. One of the original candidate pairs, catalogued as Jumbo 24, carries a piece of evidence neither side can simply dismiss: a faint but genuine radio signal detected using archived observations from a large radio telescope array, present and consistent across 3 separate observing periods spanning an entire decade. A signal that persistent is not the kind of thing background noise or a chance alignment of unrelated stars typically produces. It suggests something physically real is sitting at that location in the sky. What that something actually is: a genuine binary pair of planetary mass objects, a single unusual background star, or something else entirely, remains an open question, one astronomers are still actively investigating, using some of the same instruments that first raised the puzzle. Whether the jumbos are a new category of object or a very convincing coincidence is, as of this telling, still not resolved. Even the basic question of how many brown dwarfs exist has refused to hold still. For years, the working estimate held that brown dwarfs were nearly as common as ordinary stars throughout the galaxy, roughly one for every 3 or 4 stars in the neighborhood of our own sun, though the actual confirmed count lagged far behind that estimate, since so many of these objects are simply too faint and too cool for most surveys to catch. Earlier this year, a NASA-affiliated citizen science project called Backyard Worlds, Planet 9, changed that picture considerably. The project works by inviting ordinary volunteers, amateur astronomers, and interested members of the public with no professional training required to examine archived infrared images taken years apart by the same orbiting telescope, watching for the faint, slow crawl of an object moving against a background of more distant, effectively stationary stars, the same basic signature that first revealed WISE 0855 to Kevin Luhman back in 2014. Working through a public platform built for exactly this kind of large-scale citizen collaboration, volunteers combed through 16 years of accumulated images, some building their own custom search tools along the way, and the results, published this year, were striking. More than 3,000 new brown dwarfs, confirmed, discovered not by a small team of professional astronomers working alone, but by a broad community of volunteers sifting through public data in their own time. There is something worth noticing in exactly who made this particular discovery. Kumar and Hayashi and Nakano were trained astrophysicists working through advanced mathematics. Tata was a doctoral candidate at one of the most prestigious universities in the country. The teams behind Tide 1 and Gliese 229b were professional research groups working at major national observatories. The 3,000 new confirmations announced this year came, in large part, from people with no professional astronomy training at all, working from home, on their own time, scrolling through publicly available images because the raw data existed and somebody, eventually, needed to actually look at it. The tools for finding a brown dwarf had, over 60 years, moved from a theorist's notebook to a research team's spectrograph to an ordinary person's laptop, and the objects kept turning up at every stage, waiting, as they always had been, for someone to notice them. Other current surveys are adding to the count through yet another method entirely, watching a star's brightness for the small, precise dip that happens when an object crosses directly in front of it, blocking a tiny fraction of its light on a regular, repeating schedule. This transit method, the same one responsible for the majority of confirmed planets beyond our solar system, has recently turned up its own handful of new brown dwarfs, some in long, lazy orbits taking well over 100 days to complete, adding still more data points to a population that seems to grow every time astronomers point a new kind of instrument or an old instrument used in a new way back at the sky. 3,000 new confirmations, added to everything found in the 3 decades since Tide 1 and Gliese 229b, roughly doubled the entire known population of brown dwarfs in a single announcement, pushing the confirmed total past 6,000 objects. It is worth sitting with what that actually means. The universe did not suddenly produce 3,000 new brown dwarfs earlier this year. Every one of them had been sitting out there, unremarked, for as long as brown dwarfs have existed at all, invisible only because nobody had yet looked closely enough, with the right tool, in the right place, to notice them. The population did not change. Only how much of it we could see changed. That distinction between what is actually out there and what we have so far managed to count sits close to the center of everything this story has been circling since the very beginning. None of this is likely to be the final word. Newer infrared surveys, larger and more sensitive than anything used so far, are already being planned or are just beginning to return their first results, and each one carries the reasonable expectation of finding still more brown dwarfs, resolving still more disputed candidates, and quite possibly reopening questions that feel, for the moment, more settled than the desert or the jumbos ever were. A field this young does not stay still for long. Every boundary this story has touched, it turns out, behaves the same way once you look closely enough. The line between deuterium fusion and hydrogen fusion is real, a genuine physical threshold, but the exact mass where it falls shifts with the object's chemistry. The line between a brown dwarf and a low-mass star, so clean-looking in a textbook diagram, blurs the moment Gaia's precision is brought to bear on a single disputed companion. The line between a real, gravitationally bound pair of planetary mass objects and a coincidental alignment of background stars is, for at least one disputed pair in Orion, still being argued over as this sentence is written. Even the line between known and unknown, between a catalogue that felt essentially complete and one that had somehow missed half its members, moved by 3,000 objects in the space of a single year. Even this hour's own vocabulary carries the same fingerprint. Free-floating, companion, desert, boundary, threshold, every one of these is a word borrowed from ordinary human experience and pressed into service for something that has no experience of its own, no sense of standing alone or belonging, no awareness of scarcity or abundance. The words are useful. They let one person describe to another, in a shared language, what a telescope recorded. They were never going to be perfectly true to the thing itself, only true enough to be useful, the way any map is true enough to navigate by without ever being the actual land it describes. The same quiet correction applies more broadly than this one title suggests. Once you start looking for it, Pluto did not fail to remain a planet when astronomers redrew that particular boundary 2 decades ago. The boundary moved, Pluto did not. The astronomers who reclassified it did not erase it from the sky. They gave it, and several other similar objects discovered around the same time, a new category of their own, dwarf planet, an attempt to describe more honestly what these objects actually are, rather than force them into a box built for something else. That is not a demotion in any sense that matters to the object itself. It is bookkeeping, useful and necessary bookkeeping, conducted entirely on the human side of the telescope. A comet does not fail to become an asteroid, nor an asteroid a planet, merely because the line separating them depends on definitions astronomers argue about at conferences. The objects themselves, in every one of these cases, simply are what they are, exactly and completely, regardless of which side of a human-drawn line they happen to land on this decade. Brown dwarfs are only the clearest example this hour had room to tell, in full, not the only one the universe has on offer. None of these lines were ever handed down by the universe fully formed. Kumar did the mathematics. Tata chose the word. Astronomers drew the boundary at 13 Jupiter masses on one side and 80 on the other, because that is where a particular reaction happens to start and stop. Useful, necessary lines for organizing what would otherwise be an unbroken continuum of collapsing clouds, more massive than a moon, less massive than the smallest true star, with no natural seam running through the middle of it at all. The categories are ours. The continuum was always the universe's. Which brings the story back, finally, to its title, and to a word that has been sitting quietly at the center of this entire hour, mostly unexamined, doing exactly the work a title is supposed to do. Failed. A brown dwarf, the shorthand goes, is a star that failed. Consider, though, what that word actually requires in order to mean anything. Failure needs a goal that was not reached. It needs an attempt, a direction, something aimed at and missed. A person who trains for a race and does not finish it has failed, because running the full distance was the point, the thing being reached for. None of that description applies to a collapsing cloud of gas and dust. It was never aiming at anything. It gathered whatever mass happened to be available in its particular corner of its birth cloud, collapsed under gravity exactly as far as that mass allowed, generated exactly as much heat and pressure as physics demanded it generate, and settled into exactly the object that combination of ingredients was always going to produce. There was no attempt in any of it. There was no moment where the outcome could have gone differently and did not. Every step followed automatically and completely from the conditions that came before it. It would be easy, at this point, to object that a brown dwarf does, in some sense, try. It fuses deuterium, however briefly. It generates real heat and real light from a real nuclear reaction, the same basic process that powers every star, for however short a window that fire lasts. Does that not look like an attempt cut short? It does not, once the mechanism is understood plainly. Deuterium fusion is not a preliminary stage on the way to hydrogen fusion, a running start that came up short. It is simply what happens, automatically and without exception, whenever a large enough quantity of deuterium finds itself under enough pressure and heat, exactly the way water automatically freezes at a certain temperature and boils at another, with no attempt or intention required at either transition. A brown dwarf did not try to fuse hydrogen and manage only deuterium. It fused exactly what its particular mass made available to fuse, completely, and then stopped exactly as completely when that fuel ran out. Calling any of this a failure is not wrong the way a factual error is wrong. It is wrong the way a category error is wrong, the same kind of mistake as searching for a fixed, universal line at exactly 13 Jupiter masses and 80, and being surprised when the line will not hold still. Failure is a word built for creatures who set goals, who can fall short of them, who can imagine a different outcome and feel the gap between that outcome and the one that actually happened. A brown dwarf has no goals to fall short of. It did not almost become a star and miss. It became, completely and without any shortfall whatsoever, exactly the kind of object that 13 to 80 Jupiter masses of collapsing material under those particular conditions was always going to become. This is not a reason to feel better about brown dwarfs, as though they had been quietly misunderstood and deserved an apology. That would only be trading one human idea, failure, for another, redemption, and hanging it on the same object for the same reason. Because a story about failure and a story about quiet triumph both need the object to be a kind of character, striving or overcoming, when it was never doing either. The honest recalibration is smaller than that, and harder to sit with. The word was never really describing the brown dwarf at all. It was describing the gap between what a person, looking up, expected to see, and what was actually there. Think, for a moment, about how this particular word found its way into your evening at all. Somewhere, a person looked up at a point of light too faint to be a star, and reached, understandably, for the nearest word that seemed to fit. Failed. It is a natural word to reach for. It is also, this hour has tried to show, The wrong one, not because the object secretly succeeded by some other measure, but because success and failure were never the right instruments for measuring it in the first place, any more than a ruler is the right instrument for measuring a sound. 60. Some years is not a long time. By the standards of the universe, this story has been describing a universe old enough that if a true black dwarf could exist, we still would not have found one. A universe that built the very hydrogen inside every brown dwarf, discussed tonight inside the first few minutes of its own existence, long before there was gravity enough anywhere to gather that hydrogen into anything at all. 60-some years is, however, close to the entire length of a single human life. Everything traced across this hour, the mathematics, the name, the proof, the weather, the disputed pairs, the doubled census, fits inside a single lifetime, comfortably, with room to spare. That is worth remembering the next time a number in years sounds impressively large. Against the object being described, it rarely is. Against the person doing the describing, it very much can be. Kumar worked out the mathematics for an object nobody had ever seen. Tata gave that object a name before a single confirmed example existed anywhere in the sky. Two teams, an ocean apart, spent 20 years chasing a category that kept refusing to show itself, until an element that would not burn and a molecule that would not survive real heat finally proved it was real. The very first object either team confirmed turned out, decades later, to be quietly hiding a second one inside it. Every close look this hour has taken at a cloud band, at an aurora with no explained source, at a desert that might not be empty, at a pair of objects that might not be a pair, at a population that just doubled without the universe changing at all, has told some version of the same story. The boundary keeps moving because the boundary was never really there to begin with. Only the collapsing clouds were there. Only the mass and the gravity and whatever each one turned out to become. That is the truer ending than the one the title promises. Not a star that failed, not a story of falling short. Just matter, doing exactly what matter does under the pull of its own gravity, indifferent to the words that would later be found for it, complete in every sense that actually matters, long before anyone existed to call it anything at all. Look up again, the way this hour began. The same scattered points of light are still there, and most of them are still doing the one thing that makes a star, fusing hydrogen quietly, patiently, for billions of years. Somewhere among them, unseen, sit the ones that never crossed that particular line, cooling in the dark the way they have been cooling for longer than human civilization has existed, indifferent to the word failed and indifferent just as completely to any word that might someday replace it. The night can wait. Every quiet light above you was always exactly enough.